All right. This is covering 7.3 intervals based on normal populations, and I'm using this lecture PDF if you want to print it up to follow along. Also, I'm going to be referencing this T-table of critical values, and a link to it is right there. So I'll be referencing that as well. So let me go ahead and start. This is intervals based on normal populations. Let's see if I can get this to, hold on. Can I make it full screen? Oh, well, I'm not trying to make it full screen. I'm not going to worry about it. So usually in the real world, we don't know population standard deviation. So instead, we use the samples standard deviation. And we use an S for that. So when we do that, we are introducing two unknowns, both the sample mean and the sample standard deviation. So we have two random variables. So it turns out that this distribution follows a T distribution, not a Z. And this is the theorem from your textbook that just says when the sample mean X bar of a random sample of size n drawn from a normal distribution that has a mean mu, then this random variable t, we're going to use t not z, which is just x bar minus mu over s over square root of n, has a probability distribution called a t distribution, and it's got what we call n minus 1 degrees of freedom. So properties of this T distribution is first, like a Z, they're symmetric. It's that bell shape, centered at 0. Symmetric, centered at 0. Different sample sizes have different T distributions. The tails tend to be a little higher than normal, but as T gets bigger, shouldn't be T, my apologies, as N gets bigger, this distribution starts to approach the normal distribution. So it looks like this. Your textbook, by the way, is using this new, looks like a script V instead of degrees of freedom. I'm just used to using degrees of freedom, DF. And these are just some different T distributions. So you see they do have that bell shape. And as the numbers get bigger and bigger, the sample sizes get bigger, it starts approaching closer to a Z curve. So there's a little bit of notation here. So before we did a Z alpha, well, now different sample sizes have completely different T distributions. So when we have this alpha, we also need to include the degree of freedom. So a little bit of this notation. So we can use R to find these T values given a left side probability. So in this case, alpha is going to be the right tail. So it's the area to the right of T. So this is the alpha region. So I'm going to call that the upper tail or the right tail, and the left tail is going to be 1 minus alpha. So we're going to need these T values to do confidence intervals. So let me do it using R as an example. So if I have the upper tail area is equal to 0.025 and we have the sample size is 10, the picture that goes with this is 0.025. So this is going to be 1 minus that. 0.025 is going to give us 0.975. So this area here is 975. The sample size is 10, so the degrees of freedom is 1 less than that. I get 9. So using R, it's Q for the quartile. Since it's not a normal distribution, it's a T distribution. We use T, and then we need to do the left tail area and then the degree of freedom. And this is the printout if you did R. So you can be using R to find these critical T values if you're not. There's also some tables that can give us these criticals. So for certain alphas and certain degrees of freedom, we can find these certain critical T values from a table. And we're going to be using these for confidence intervals. So this table isn't the one in your that's in your textbook. It's one from another class I'm teaching. I kind of like it better than the one you're given. So for here, the picture we had above, this, if I had, for what I just did, this was 0.025. Now remember, when we're doing confidence intervals, we want that same on both sides. So this side would be 0.25, and together that adds up to 5%. So this middle is 95%. So this would be for a 95%. So on this table, they're showing it like this. So be careful. Your author is calling this whole thing alpha. But if we use this table when we go to do confidence intervals to find these critical T values, in my opinion, they're actually easier. So the one we just did, we had a degree of freedom of 9. So my degree of freedom was 9. And with this tail being 0.25, and this tail are 0.25, that's going to leave me with a 95% confidence interval. So to read these tables, and that was the table I showed at the beginning, that is, you can find this table right here, T table of critical values. So we've got 95% confidence level. The degree of freedom was 9, so go to row 9. And right here, do you see you get that 262? So you can read these things off directly from this table, or you can use R. This was using R, I got 2.262. Using the table, I got 2.262. So it's totally up to you. If you actually do look at these tables, let me go show you the whole table. We had this 95 column. I can't really show it to you here, but at the very, very bottom, do you see the one-sided? It has 0.25 at the very bottom. There's the 0.25, oops, at the very bottom. So those alphas are at the very bottom, but I'm probably confusing the heck out of you, but hopefully it'll become clearer as we go. So here's an example. So using this for confidence intervals. So remember, for Z's, when we were using a normal, if we knew sigma, population standard deviation, our confidence interval would be x bar plus or minus that critical Z value, sigma over square root of n. And we would use the Z table to find that critical Z. For now, since I'm using S instead, what's going to happen now is my confidence interval is still going to be x bar plus or minus, but rather than use a Z, I'm going to use the T. I don't know sigma, so I'm going to use the sample standard deviation instead over square root of n. So here we go. So it's just like what we did in 7.1 and 7.2, but now we're using a T distribution instead of a Z, and a sample standard deviation, S, instead of a population standard deviation, sigma. So here we want to estimate the mean commute time of students to San Francisco State. We have a random sample of 30, so N is 30. The mean commute time was 35.4, so the sample mean was 35.4. And the sample standard deviation was 8. So we want to find a 95% confidence interval, so 95% confidence interval. So we need to find T star. So if we use R, we have to think really quick what this is going to be. If this middle is 95, then each of the two regions are half of 5%. So that upper tail is going to be 0.25. So we want to use QT, since this is a T distribution, of 0.975. That's this whole area is 0.975. And then since n is 30, my degree of freedom is 30 minus 1, which is 29. So we're going to go 29. And if you use R, I did this already, it's going to spit out 2.04523. And this is using R. Now, if you use the table, so let me go to the table real quick. Let me get to the table. I have the table here. So we want to go, since the degree of freedom was 29, we want to look at row 29. Oops, sorry. See if I can do a little screen capture of it. Oops, not letting me do a little screen capture. I don't know if you can see this. If you go to row 29, I have no way of highlighting this. My apologies. But if you look at row 29 and you look at the column for 95%, I hope you can see that you get 2.045 using this table. So row 29, the 95%, you get 2.045. So let me go back. So using that table C, row 29, the column for 95%, the T star you get for this is 2.045. So you have two ways you can find these critical T values. It's up to you which one you prefer. So for this one, my margin of error, which is T star S over square root of N, 2.045. S happens to be 8. The sample size is 30. And so I get 2.9869. And I'm going to round to 2 decimal places. And so my confidence interval, which is X bar plus or minus my margin of error, my sample average is 35.1 plus or minus my margin of error, which is 2.99. And if I do 35.4 minus 2.99, I get 32.41. And if I add 2.99, I get 38.39. So this is how we can use these to find confidence intervals. So a couple things to pay attention to that are important is if your sample size n is less than 40, we need to verify the population distribution is approximately normal. In order for these calculations to apply, otherwise it might not follow this T distribution. And we're going to use the fact that a random sample distribution tends to be similar to the population's distribution. And so when n is less than 30, we can look at the samples. We can create a histogram or a stem plot. We can do one of those QQ norm plots, those normal quantile plots. Or maybe a box plot. We can do all of these, just a few of these, but this is how we can check to see if we think that it's reasonable to assume the population distribution is normal. So let me go ahead and do this, and we're going to use R to do all of our calculations for us, to do a little graphs for us, to check these things. So here's 2 quick examples, doing the whole thing. So this is the first example. It's right out of your text. And this was a study of the ability of individuals to walk in a straight line was reported. And this data looked at your cadence, strides per second for a sample of 20, N is 20 randomly selected healthy men. This is our data. So I went ahead and put it into R. And this was the code that I used in R. And then I said, let's make a histogram of the data, let's make a box plot of the data, and let's go ahead and do one of those normal quantile plots. And then looking at that, we can answer the question, is it reasonable to assume that the population distribution is approximately normal? Well, if we look at the histogram, I'd say that this is approximately a normal shape. We got that bell curve going on there. I look at this and, hey, I'm seeing that there doesn't look like much skewness. This is approximately symmetric. You know, it's a little skewed, but for the most part, that's not too far off. And then the dots do follow relatively close to a straight line. So yes, it's reasonable for all those to assume that the population distribution is approximately normal. So then I said, all right. So then I went to R, and I said, well, let me find the mean. So this was my X bar. I said, let's find the standard deviation, S. And then while I was at it, I said, I want to do a 90% confidence interval. So remember, if this is 90, then the two tails are 10%. So each half is 5 and 5. So this area is 95, and N is 20, so my degrees of freedom are one less than that, get 19. Now if I wanted to use the table on the table C, I would do row 19, and then I would do the 90% confidence level column. So I'm going to go switch to that really quick. Hopefully focus on row 19. So row 19 is right here. Here's row 19. And we want the 90%. So I'm going to zoom back out. So 90% is this column right here. There's the 90% column. So if we look at where the 19 row and the 90%, I see this 1.729. So I got 1.729. So either way you want to do it, I don't care. So either way, so M is going to be the T star, S over square root of N. So 1.729 times S, 0.0765. There are 20 data values. I get 0.02957, which is approximately 0.03. And so my confidence interval is X bar plus or minus M, which is 0.918 plus or minus. And I'll round that to 3 decimals, which is that 030. And then if I take 9.918 and subtract 030, I get 888. And if I add 030, I get 948. So that would be the confidence. We would estimate that the average cadence for men is somewhere between 0.888 and 0.948. So let me just do one more quick example using R. So this one here is we have computers in some vehicles calculate various quantities related to performance. One of these is the fuel, should be a fuel efficiency of gas mileage in miles per gallon. Lots of typos here, sorry. For one vehicle equipped in this way, the MPG were recorded each time the gas tank was filled, and then the computer was reset. Here, oh my goodness, here are the MPG for a random sample of 18 of them. So for this one, N is 18. So my degree of freedom is 1 less than that. It's always, the degree of freedom is always 1 less than the sample size. And then it just says the questions are, is it reasonable to assume the distribution of all MPGs follow an approximately normal distribution? And then let's do a 95% confidence interval. So I went ahead and used R. I plugged the data, I created a data set in R, there it is. And this time I decided to do a stem plot rather than a histogram, just for the heck of it. So I did a stem plot, a box plot, a QQ norm. I went ahead and threw the QQ line in, and then I said, hey, let's find the mean and let's find the standard deviation, and this was what it printed out. So I can look at my stem plot. Yeah, that's approximately symmetric. That works. I see this is my box plot is looking roughly symmetric as well. And the dots aren't too far from, dots follow a straight line, approximately. Straight, not safe, sorry, straight line. So to answer question 1, I would say that yes. Or question, is it A or A? Question A, I'd say yes. Reasonable to assume normal. Population distribution is approximately normal. And then now we want to do a 95% confidence interval. So for this one, I already said my degree of freedom was 17, one less than our sample size. So I'm going to go ahead and use the table. Personally, I think the table is easier. So if I go to the table, I want to look at row 17, always the row of the degree of freedom, and the 95% column. So I'm going to switch over. So we want, here's row 17, so go row 17, and then the column for 95. And when I do that, let's see if I can, I don't think I can highlight it. When I do this, I get 2.110. I don't know how to highlight this. So 17, row, column 95, 2.110. Column 95%. And so the critical T that works, if you wanted to look at a little picture, what this is telling me is this is 2.110. This is minus 2.110. This is 0.95. This region is 0.25, and this region is 0.25. And this is for degree of freedom 17. So if you wanted the picture that goes with these are the T's. So for this one, my M is T star S divided by square root of N. So the T I want to use now is 110. My S, I calculated up here, which is 4.298. My sample size is 18, because I have 18 data values. This gives me 2.1957, which I'm going to round to 2.20. So my confidence interval, which is X bar plus or minus M, ignore this. Oops, I think I made a boo-boo. I think these are the wrong ones. I had changed this, so my apologies. So this is my X bar. So my X bar is going to be 42.61 plus or minus 2.20. And if I put it in interval form, 42.61 minus 2.2, this is 40.41. And if I add 2.20, I get 44.81. So you only have a couple of problems for this section. This is just what we tend to do in the real world because we don't know the population standard deviation. So that means we have to use a different distribution rather than Z, we have to do T. And it's not the same T, it varies depending on the sample size. So if you have any questions, let me know. Good luck with the homework. I think that's all of it. Yes. Have a good Thanksgiving.